Hello physics students. Welcome to our fourth and final video on Ampere's law and our 13th and final video on this long topic of magnetism. So in today's video, you'll be learning how to find the magnetic field for current densities that are not constant. Up until now, we've been looking at analyzing currents that are spread evenly throughout a conducting cross-section. But today, what we're going to look at is finding the magnetic field for a function of current density. So as you can see here, we've got some current density constant, and then at radius 0, this is, by the way, a cylindrical conductor, at radius equals 0, the current density is 1 times J0. But as R gets closer and closer to capital R, the current density gets smaller and smaller until we get to the outer edge of the conductor at capital R, where we have 1, -1, or 0 current density. So the current density plotted looks like this. The flow is most concentrated at the middle of the conductor, and then it gradually gets less and less, and at the outer edge we don't have any electrons flowing at all. So what we're going to do is find the magnetic field inside this conductor for R less than capital R, and outside the conductor for R greater than capital R. Now you may already remember from Gauss's law charge densities that were not constant. What this means is that we're going to have to actually perform an integral more complicated than the integral of just B ds becoming B times the a length of our Amperian loop. So that's what's coming. So let me create a pause to give you an opportunity to copy this down. All right, so let's move on. So as I said, we begin inside the conductor for R less than capital R. We begin with Ampere's law. Now, of course, the loop is going to be some circle less than the radius of the conductor, because we want to find the magnetic field along this Amperian loop. So that is the loop we're using, a circle, matching the symmetry of our conductor. So we go on, and the left side is still B times 2 pi R, because even though this current is not constant, it's still radially symmetric, which means that the magnetic field, if the current's coming out of the board, will still be going around this like this along the Amperian loop, and a constant value. So that's why this integral just becomes B times the circumference of our Amperian loop. But on the right side, we still have mu0 I enclosed, because we cannot say that I enclosed does not equal J times area, because the J is a function, not a numerical constant or a number value. So what we have to do is take a detour to determine this I enclosed. And so we can't use J times area for I enclosed for the entire conductor, but if we pick an area that's small enough where the current density is approximately constant, we still can use that concept that current is J times area, but we have to pick our area in a special way. So what I do is I pick an area that's like a ring, very thin. It's got a thickness here of dr. I don't know if you could see, that's kind of small. And so notice that the R, since dr is so small, the current density will not vary much over that ring. So we can say I equals J times area for that tiny ring. But we don't want just the current in this tiny ring. What we want is the current of the entire current inside of our Amperian loop, so we're ultimately going to have to integrate. So let's fill in the pieces and then integrate. J, we take our function, it's right here, but the area of this little ring we can calculate from the area of a rectangle, because we could imagine if this were made of putty and we sliced it and we opened it up, it would have turned into a rectangle, and so we could determine the area of this where the current's going through is base times height. base, the circumference of the circle, 2 pi r is that length, times the height of the rectangle, which is dr. So the thing that changes from all these problems is this part right here. But this dA, 2 pi r dr, for cylindrical conductors will always be the same, but this function changes, so the integral answer will be different. All right, so now we're going to add up all the currents in all the rings, starting from a small ring out to our Amperian loop. In other words, we're going to add up or integrate from a small ring, a tiny one of radius approximately 0, up to our Amperian loop. And then what I did is I just put all the constants together here, and then lumped the r variables here, and I got my dr. So what I'm integrating is this r dr, which is r squared over 2, add 1 to the exponent, divide. And then I'm integrating this r cubed over r squared term, so I add 1 to the exponent, make r to the 4th, and then divide by that new exponent 4, and I still have the r squared there. And I'm going to evaluate that for those limits. So let me create a pause to allow you to copy this down. Let's move on. Let's plug in the limits now. So I plug in first the top limit, the radius of our Amperian loop, into our function, and then the other limit 0 into our function here. And so those are those terms there. And so there is the current inside of our Amperian loop right there. So now that I have I enclosed, I could end my detour and come back to here and plug in that I enclosed so I could solve for B, which is what I've done here. So I've got my B 2 pi r over here, and then the mu 0 right there, and then the I enclosed all of this after there. So the 2 pi's go away, as does one of the radii, r to the 1 instead of r squared, r to the 3rd instead of r to the 4th, and then I also took out 1/2 over here just to, I don't know, I guess I didn't have to do that, but I thought it would look a little nicer. So there it is, the magnetic field inside this conductor. Notice at radius 0, it is 0, the magnetic field at the center of the conductor, and then it increases from there. We'll talk about that later. All right, so let me create a pause to allow you to copy this down. Let's move on. So that was the magnetic field for r less than capital R inside of the conductor. Now we want to find the magnetic field outside the conductor. So let me make a little room. All right, so R greater than capital R. So once again, I begin with Ampere's loop, Ampere's law. Again, a reminder, all these terms are important. The vector signs, the dot product, the circle, and the integral. Don't leave any of those off, otherwise you say something radically different. The left side, if we make an Amperian loop like this, the magnetic field will still run along the Amperian loop. It'll still be a constant all along the Amperian loop, so this just becomes B times the circumference. But once again, we cannot say that this is J times area because the J is not a constant. So we need a detour again. Let me make a little bit more space. Now, you might be thinking, oh, we've got to do this whole thing over. Not really, because we could recycle the integral. Basically, the thinking will be the same. The setup, we're making a little ring, we're going to find the current in that little ring, then we're going to integrate to find the current of all the rings added together. So we would be doing the same exact analysis. The only thing is, we would not stop before we got to the outer edge of the conductor. We would keep on integrating all the way to the outer edge to get the I enclosed. When we make an Amperian loop around the whole conductor, we'd integrate all the way to capital R. So that's what we're going to do, is we're going to just recycle this formula. So So we're just going to integrate from 0 to capital R. So we could go right here and say that I enclosed is from 0 to capital R. So I just took this formula right here, rewrote it, and changed the limit for plugging in. So now I just have to plug in that new limit. And there it is. I plug in capital R first, here and here. That's what's here and here. And then I plug in 0 next there and there, which makes just 0 minus 0. So let me simplify that a little bit. Okay, so, let me create a pause in case you need an opportunity to copy these notes down to catch up. All right, so what I can do is this simplifies to r squared over 2 minus r squared over 4. All right, this r to the 4th and r squared I could simplify like that. So what I can call this is 2 over 4 minus 1 over 4, which gives me just 1 over 4, r squared over 4. So I enclosed which okay, so there, now I can say that's the end of my detour, and I can go back to Ampere's law right here and plug that I enclosed in there. So let's mark this at the end of our detour. And fill this in. The I enclosed right there. So the pi's go away, and then I can have the 2 divided by the 1/2 divided by 2, which puts 4 in the denominator, and I get the magnetic field as mu 0 Okay, so let me create a pause to give you a chance to catch up if you need it. All right, now I just realized I forgot to do unit check over on the previous formula, and I'm going to do a unit check on this formula. So first of all, this formula here, unit check, remember, has to match the units of mu 0 I, which is in amps, over 2 pi r, which is the r is in meters. So do I have that here? Well, what I have is the mu 0. Then I've got amps per meter squared. That's J0 times a meter squared all over meters. And if you look at that, those meters squared cancel, so it gives me mu 0 amps over meters. The units match, so the formula appears to have at least the right form. So let's take a look at this formula. Let's see if I could catch any mistakes here. So again, we're comparing it to mu 0 amps over meters. That's the units that we need. We've got our mu 0 here. Then this is amps per meter squared, J0. And then what I have over here is meters minus meters cubed over meters squared, which is just meters. So I have overall meters here. By the way, another way you could discover an error is something like this. If we had in the parentheses here meters minus something that had no units, that doesn't make sense. You can only subtract meters from meters. Okay, so then we would know, wait a minute, something's wrong with one of these powers over here. Either this is to the 1 power or this is cubed. We go back and find our error. So, you know, another way you could see unit errors, and when there's additions or subtractions that don't have the same units, then you know there's an error in one of those terms. But overall, this Prenti term has units of meters, and you see that we ultimately simplify to the correct units. All right, well, there's one last thing that I want to do to finish off this nice, wonderful example, and that's to create a graph, okay? Always nice to see the patterns shown in graphical form. So let's make some axes. This is our radius r. Here is the edge of the conductor. Here we're inside the conductor. Here we're outside the conductor. So, and this is going to be our b. Okay, and so originally for r less than r, it's this function. It's going to be some kind of curve because of the r cubed. Question is it concave up or concave down? Again, not that critical that you know, but if you really are like a perfectionist with these graphs, you could just take the r dependence here. R minus r cubed is the essence of that function right there, right? All the other things are constant. Quickly do the derivative twice. What you get is 1 minus 3r squared. There's the first derivative. Take another derivative. This is 0. So what we have is minus 6r to the 1 power. That's a negative second derivative. The function here is concave down. So concave down, we're going to go like this. We're going to reach some kind of constant or some kind of peak value over here. And then from here, we have the standard 1 over r graph because everything is constant but the 1 over r. So at twice the radius, we should have half the value. So some kind of descending curve like that. And to just to, you know, make sure that the pattern is apparent, that it's a downward curve. And then the peak value, well, I could plug in capital R into either of these formulas. This one would be obviously easier. So that turns out to be mu 0 J0 R over 4 is the peak value right there, okay? All right, so let me create a pause to give you a chance to copy the graph down. All right, so that's our last, fourth and final installment of Ampere's law. And as I said, the last video for the magnetism topic. So congratulations for getting through a big, beautiful topic. So I just want to remind you again that for non-constant current densities, what you have to do is you have to integrate, actually perform an integral. Of course, in Ampere's law, there is an integral, but it just turns into this b times 2 pi r, so it's always easy. But the I enclosed, there will be some function to integrate, and essentially, I guess it's erased at this point, but what you have is the j function times dA, and the dA is always 2 pi r dr, a rectangle, 2 pi r, the width, and the height dr, 2 pi r dr is the area, times the j, and then you integrate that for your answer for the I enclosed. All right, so I hope you enjoyed the video. I hope you learned a lot. I hope you learned a lot in the magnetism topic and that you enjoyed the magnetism topic because it is now completed. So I will see you in the next topic, the next physics video.